Okay.
We're showing the presentation. It's fine. It's fine.
Whatever is happening is happening.
Yeah, so the video will be here, but you will hear. Go ahead. What happened to the last time he showed up all my eyes.
Just most of the
The first sentence I don't
So I'm wrong.
I don't care what the type of it is, what's there. I just add up all the matter. No, I think that we saw
and then discuss it.
put it on the
just go to where live.
yeah, and the other YouTube video. Most
Right? Oh, come on. I'm really tired. I'm not enough. Can't you tell? I'm really not awake. I can't go there. I'll listen to a single word you're saying. I might just sing that. If I can't get it built off, I'm sorry.
We do. Yeah, I can feel it.
Yeah, because they said that they got a computer and I know you guys stay. We're also wondering if we have to leave.
okay.
Sitting there. Crazy Tuesday.
Possibly my own
They're gewoon
yeah, I replaced the I know as soon as I start saying that, it's going to break.
Actually, you can turn this trip. You can take this one.
Where's the girl?
She got some bad news that her uncle probably leave after.
It's so many, we never have so many people on Tuesdays.
Really?
Tuesday is the only day we have empty days. It's such a good job of advertising that. You're gonna be speaking as well one day.
One day.
Come on,
Maybe.
you have to tell your own to back to the
Yeah, I think after once I submit my thesis, I'll probably do it.
yeah. Next week it's gonna get So let's make it, but yeah. Let's take another chair.
Okay, so if no one is asking a question at the beginning, you two are in charge of asking a question. Simple. No,
Yeah.
no astronomer, not an astronomer, but general. So no one needs to know that you're an astronomer.
You just ask like, so is the sun gonna hit the air?
Exactly, yes. Are we gonna die?
Yeah.
About those questions in your article.
So
just
I've
in
heard.
case.
But maybe we can ask share
I went to the gym and then I came here. Well, I went home at 8 and then I came here.
down.
No, I think it's one of our friends left today. Yeah, but he went for a postdoc in Sardinia. And I helped him out move and stuff. Now it's like, I'm just gonna keep this box and be like, no, you don't go.
Which one do I know?
Alessandro? I don't think he came. He wouldn't come.
All of these people here. I like the support. They're gonna be like, Angus, you are. This is wrong. We all love it.
Like I said, you're being podcast live onto the internet. No, but the one that is picking the language.
Oh. Angus, you're such an asshole. I hate you.
Much appreciated. With friends like me,
We can't say anything stupid no more.
It's gonna be quiet.
It doesn't work like that. You know, you dirty motherfucker.
Only John.
Ready?
Like with the skydiving, I thought I was ready, but then when I actually started, I noticed I'm not ready.
We guarantee that you will enjoy it. Good evening. Thank you for being here. My name is Elaine. I am a postdoctoral researcher at the Argelander-Institut for Astronomy at the University of Bonn. And I am the founder of Astronomy and Tap Bonn. And here today we will present to you our event along with 7 more people, some of whom will give you 2 spectacular talks. And there will be also a translation in German. Now.
Ja, guten Tag und herzlich willkommen hier bei Astronomy und Tap Bonn. Ich bin Laila, ich bin eine Doktorandin am Argelander-Institut für Astronomie und ja, gemeinsam mit 7 anderen Astronomen helfe ich bei der Organisation hier mit und wir werden heute 2 wundervolle Vorträge hören.
So, Astronomy on Tap started in New York City by professional astronomers that wanted to share what they want, their science, to the public in a very relaxed environment. So what a better place than a pub? And here we are. So cheers, everyone, and let's go. Woohoo!
Ja, Astronomy on Tap wurde in New York gegründet von professionellen Astronomen, die ihre Wissenschaft dem Publikum weitergeben wollten in einer entspannten Atmosphäre, am besten eben in einem Pub. Wir sind eine von ganz vielen Locations, die ihr hier auch auf der Karte sehen könnt und ja, darum sind wir hier.
Astronomy on Tap will be held on every Tuesday of every month here at the Fiddlers pub, apart from December, which will be on the 3rd Tuesday because we want to avoid Christmas.
Genau, Astronomy on Tap Bonn wird immer am letzten Dienstag eines Monats stattfinden, außer im Dezember. Da verschieben wir es auf den 3. Dienstag, damit wir nicht am Weihnachten.
So, our first talk is by Dr. Angus Wright, sitting over there. Dr. Wright is also a postdoctoral researcher at the Argelander-Institut, and he has been working there since late 2016. Prior to moving to Bonn, he completed his PhD on the distribution of mass in galaxies at the University of Western Australia. Today he will talk to us about the science behind looking for life beyond Earth. I don't know about you, but I'm very excited to see what he has prepared.
Ja, unser erster Vortrag heute ist von Dr. Angus Wright. Dr. Wright ist ein Postdoc am Argelander-Institut und arbeitet dort seit 2016. Seine Doktorarbeit schrieb er über die Massenverteilung in Galaxien an der University of Western Australia und heute wird er über die Suche nach Leben außerhalb der Erde reden. Wir sind schon sehr gespannt, was er uns zu erzählen hat.
So, without further ado, Dr. Angus Wright.
Thanks very much, Eleni. And indeed, thank you all for coming. It's absolutely fantastic to see so many people here for the very first Astronomy on Tap. As Eleni said, I'm going to be talking to you guys about looking for life on other planets. Specifically, though, I'm not going to spend my time sort of doing a sort of where's Waldo of where is ET and why haven't we found him or her yet. But rather, what I'm going to be talking to you about is more what, as astronomers, we think about when we think about searching for life, searching for extraterrestrial intelligence, what we call SETI. But in order to talk about extraterrestrial intelligence, in order to talk about searching for life elsewhere, we need to kind of begin by first understanding where we sit in the grand scheme of things, the grand scheme of the Milky Way of the universe. So that's where I'm going to start with us today. And so this is it. This is home. This is the Milky Way, or rather, this is the best estimate that we have of the structure of the Milky Way, according to all of the latest research being done in that area. We're just here in what's called the Orion spur of the Sagittarius arm of the Milky Way. And it's precisely because we are where we are that we don't know for certain if this is exactly what the Milky Way looks like. And the reason is because when we look at other galaxies, their structure is very apparent. We can see that, for example, Andromeda at the bottom and the Pinwheel galaxy at the top have a whole host of spiral arms. We can see how tightly they're wound. We can see the colour of these galaxies over their entire distribution. But when we look at our own galaxy, we can't see those direct details immediately. And the reason for that is because we see our own galaxy from a very, very different perspective to what we see other galaxies, namely this perspective. This is the Milky Way as we see it. And the reason is simply because we are embedded within the Milky Way. And the outcome of that is not that we can't tell what the structure of the Milky Way is. It just means that we have to be a little bit more conscientious in figuring out how we determine the structure of the Milky Way. But more than just being edge on to the Milky Way, there is another additional problem that makes it quite difficult to determine the shape and the structure of the Milky Way. And that's that because we are where we are in the galaxy, our understanding of parts of the Milky Way is being blocked by the fact that the Milky Way is right in our face. We're being blocked from seeing the distant parts of the Milky Way by the structures that are in the foreground. So there's a neat way of thinking about this. Imagine that you're going to a huge art fair entirely about umbrellas. And when you go to this thing, you hear that this umbrella show is going to be absolutely fantastic. So you try and get there a couple million years early, and you find your spot, you sit down, and just before the entire show begins, one of the umbrellas opens up right in your face, right? Now, bear with me here. Now, it's great, and you're really happy that you can see one of the umbrellas, but you'd kind of also like to be able to see the other umbrellas, right? No, I see people nodding over here. That's what I like to say. Right. And so essentially, we're being blocked from parts of the Milky Way. That was a very convoluted example. Bear with me. All right. So this is the Milky Way as we see it. This is a picture from a survey called Gaia, and it's the deepest or the most thorough survey of the local area of the Milky Way that we've done to date. But even with an extremely new, recent, and thorough and deep understanding of the Milky Way, we still only probe about 1% of the Milky Way stars. And they occupy roughly this sort of area here. And part of the reason for that is because when you try and look deeper, you see so many stars that they start to get in each other's way. The density of them is so high that we can't actually continue to see what we're trying to see. And the other reason is because, like what I just said, we have all these big streaks of dust and things like that that are in the way, blocking our view of other parts of the galaxy. But nonetheless, even with what we can see, we can estimate the number of stars that there are present in the Milky Way. And that estimate is currently between 100 and 400 billion stars in our galaxy alone. And this fact brings up another problem. But it's not an astronomical problem, it's a human problem. And that problem specifically is that of large numbers. The human brain, put simply, is fundamentally incapable of comprehending large numbers. The way in which it functions does not allow us to do that. And so, in order to sort of understand this a little bit, I'm going to start by everyone just kind of imagine an arbitrary object. It doesn't matter what it is, be a coin or a potato or whatever. Just imagine that one object, see it in your mind. Now I want you to see 1 billion of those objects, just in a big pile, right? Everyone got that visualization in their heads? Right, that pile that you can see in front of you, that mound of 1 billion objects, is absolutely too small, right? Fundamentally too small. And there's a really simple way of demonstrating this that was going around recently on social media. And that's the following. Everyone knows what the period of 1 second is, right? That's something we deal with on a daily basis. I'm now going to tell you that 1 million seconds is about 11 and a half hours, okay? I now want you to guess, from knowing that fact, how long 1 billion seconds is. And we're going to do a very simple straw poll. I'm going to get people to raise their hands, okay? Who thinks that 1 billion seconds is less than a month? Okay, couple. Who thinks it's less than a year? Okay, a few more. Who thinks it's less than 10 years? Okay. Who's too introverted to raise their hand in a public setting? Excellent. Fantastic. That's what I'm talking about. Right. So 1 billion seconds is just over 31 years. Right? And that is just it's a simple way of understanding or of demonstrating that the human brain just doesn't function when it comes to large numbers. And it also explains and it also demonstrates how difficult it is to discuss these sorts of numbers with people, to discuss these things and visualize these things in a day-to-day discussion like we're having here. If we had, so the Milky Way has 100 billion stars. If we had a stack of paper that was 100 billion sheets tall, then the men and women aboard the International Space Station could reach out and take a piece of paper off the pile, and that piece of paper wouldn't even be 1/10 of the way to the top. If that stack was made of Lego bricks that are 9 millimeters tall, that pile would extend 2.5 times the distance to the moon. Right? So in summary, stars. Yeah. Right? Lots and lots of stars in the Milky Way. But why are we talking about this, right? What does that even matter? Stars aren't the reason that we're here. Stars aren't the reason that we want to talk about this stuff. We want to talk about extraterrestrial intelligence. But stars are a really good starting point because they give us a good idea of the sorts of numbers that we're dealing with. They give us a good idea about where we sit in the grand scheme of things and where we sit in the galaxy. We now want to start folding in other details. We now want to start talking about other important factors that are important when we start thinking about extraterrestrial life. And we have developed over a very, very long time an excellent means of adding in additional details to these sorts of things. But unfortunately,
I'm afraid we need to use
I'm afraid we need to use math, was the joke. Right, so this is what's known as the Drake equation. It was developed by a guy called Frank Drake, an astronomer, and it's a really, really good way of quantifying the number of detectable extraterrestrial civilizations that we expect to find in the Milky Way. Okay? Now it looks a little bit fearsome, but it can actually be broken up into four reasonably simple, sort of understandable parts. And so we're going to look at these four understandable parts one at a time. The first chunk, the first three terms, can loosely be described as explaining the number of habitable Earths that there are present in the Milky Way at any one time. Okay? So recently, as of today, there are over 3,800 known exoplanets in the Milky Way galaxy. 10 years ago, it was a tenth of that. It was 340. And 20 years ago, we knew 15 exoplanets total. The reason, or part of the reason, for this extreme explosion in the number of known exoplanets was a survey that was called Kepler. And Kepler, or a mission rather, called Kepler. And Kepler's goal was to try and Perfect. Kepler's mission was to try and look at a particular point in the sky. It occupied 0.25% of the sky. And in that particular part of the night sky, to try and measure the dimming of stars that was caused by planets passing in front of them. And because of Kepler, we now have, or largely because of Kepler, we now have this unbelievable quantity of exoplanets. But more than that, we can use the results of Kepler to estimate how many planets there are per star. And the results that exoplanetary scientists have at the moment is that there is roughly, on average, one planet per star in the Milky Way. But it's not just planets per star that they were interested in. They're interested in more sort of SETI-like goals of Earth-like planets in Earth-like situations around Sun-like stars. Okay? And what that means is that they were looking for sort of Earth-sized planets in what we call the habitable zone of Sun-like stars. And the habitable zone is this sort of region around any star where, because of both the brightness of the star and the amount of light that reaches the planet, and because of the greenhouse gas effect on a planet's surface, a planet could hold liquid water on its surface. Because as we know it, life needs liquid water. And so Kepler searched for for possible Earth-like planets around Sun-like stars. And what they found was that around Sun-like stars, 1 out of every 6 stars likely held an Earth-like planet. 1 in 6. But in the context of what we're talking about, that doesn't actually completely cover the story. We want to know, with these 3 terms at the beginning of our Drake equation, what the fraction of habitable Earths is. And that doesn't just mean it could hold liquid water. It means that it needs to be able to support life. It means it has to have liquid water. It has to have a magnetic field emanating from its core to stop the atmosphere being stripped away, and a lot of other things. And so these 3 numbers encode all of that information. And that's the first chunk that we talk about in the Drake equation. The second chunk is the fraction of those habitable Earths that actually go on to form life. And this number is very, very difficult to pin down. And the reason it's difficult to pin down is because we currently have 1 example of life existing on an Earth-like planet that is habitable, and it's us. And so essentially the best estimate that we can put on this particular parameter is that it's definitely not zero. And that's pretty much it. Right? The optimist would say, hey, we're an Earth-like planet and we form life. Make that baby one. Right? But a pessimist might say the opposite. We're a freak occurrence. That's essentially zero. Right? We'll get more to that a bit later. The third part of this equation is to do with the fraction of that life which formed that then goes on to be able to transmit its presence to the rest of the galaxy. In the Milky Way, currently, or on Earth rather, currently, we have a huge gamut of life. Life goes all the way from the simplest of organisms, single-cellular organisms, through to multicellular organisms and small microscopic animals like plankton that create these beautiful bioluminescent tides all over the world, all the way through to us. But in the context of these two numbers, the only ones that matter are those which can transmit their presence to the outside galaxy, the outside universe. And that alone is us. Right? So these two numbers may not be anywhere near one, right? Given that we're the only animals that have created the telescope. And what that means is that every different non-communicating life form on the planet, every single animal that just cannot communicate with other intelligent beings.
Very up to date.
Does it? It was a cheap shot, I know. They don't qualify as life in this equation. The last factor that's relevant to us, or that's important in this equation, is this L term. The L term is the time period that a civilization that is able to communicate with the outside universe continues to do so. Right? And this is not, I mean, you might naively think that this is an infinite number. That as soon as you begin to be able to create radio waves and send them into space, then you do so for the rest of eternity. At the upper limit, this is probably limited by the lifetime of a star. So a couple tens of billions of years, right? Because if your star explodes and the planet goes with it, then you're no longer going to be communicating your presence to the outside world. But in reality, we expect this number to be significantly lower. And the reason why we expect this number to be significantly lower is typically grouped into two possible main outcomes. The first of which is that civilizations destroy themselves, and the second of which is that they become so technologically advanced that reality ceases to be worthwhile, and that they go into a virtual reality and stop caring about the universe. And in both of those cases, signals stop. And now what that number is up for a lot of conjecture, and it actually leads us very nicely into the next one, which is that when we put all of this together, we get the result of the Drake equation, which is the number of civilizations we expect to be communicating with us from within the galaxy. And now, if we're an optimist, like I am, then we say we have one Earth-like planet produced every year. Life always forms, and that life always becomes intelligent, and it always begins to communicate. Then what that means is the number of sentient, intelligent, transmitting life forms in our galaxy is just determined by this L number. And if that L number is 1 million, then there should be 1 million civilizations in the Milky Way alone screaming into the void, trying to get our attention, just like we are to everyone else. But there is a significant problem with that idea, and that is the reality of our observations. Despite all of our searches, we have currently found 3 intelligent life. No, I'm kidding. We have currently found no signs of communicating intelligent life anywhere in the galaxy. And this discontinuity between what we expect and what we find is frequently referred to as the Fermi Paradox. There are many solutions that people have proposed to the Fermi Paradox, 2 of which are probably the most sensible, and you can group most of them within these 2 categories. The first of which is we are alone. We are the only intelligent life that exists in the galaxy. And this is what we call the rare Earth hypothesis. And the justification of the rare Earth hypothesis is that the reason we are alone is because one of these factors, one of the first 3 factors, is infinitesimally likely. It's infinitely unlikely. And we are a fluke. And therefore, it's entirely reasonable to expect that there will never be another fluke. Right? The second possible solution, the one that I personally think is probably more likely, has to do with this L value. And it is this. Life evolves too quickly for its own good when it comes to seeking out other life. And the idea is essentially this. And the reason I think that this is justifiable is just by looking around. So take the Earth as an example. We first developed radio communication. The first long-distance radio communication was made in 1901. Since 1901, we've been transmitting information out into the void. How long do we think that the span of our transmissions will continue before we inevitably no longer communicate for one of these 2 reasons? Let's just go with a couple thousand years. And I think a couple thousand years might be generous. And the reason I think that is by looking around. Since 1901, we could look at nuclear weapons, as this cartoonist has done. But more likely, since 1901, we've unequivocally and possibly irrevocably changed the climate of our planet. You extrapolate that another 2,000 years, and who knows? But you don't have to be a pessimist either, right? You can go the other way. You can say, oh, that's just a blip, we'll figure that out, no worries, right? Paris Climate Accord, right? And you can say, what happened in the last 120 years technologically? Since we created the first telecommunication, whoop, I went back. Since we created the first radio transmission, we've developed supercomputers. We've developed robotic rockets. And we've pushed the boundaries, or started to push the boundaries of what we think about artificial intelligence. Is it so hard to believe that in 2,000 years, we will have created a technology so advanced that virtual reality begins to become preferable to actual reality? And if that does sound fantastical to you, it does sound like a fantasy, then I offer you to consider this. Today, in Guangzhou, China, there is a virtual reality zoo. There is a zoo where they have realized that it is preferable for people's enjoyment to have virtual animals than real ones. And it's because people get to interact more, and it's much easier for them because you don't have all that fuss of keeping animals in captivity. It's a much easier business model. They keep one server. You ever try running a zoo with one animal? And so this isn't necessarily a fantastical idea. And so if we think about our 2,000 years, we think about the 2,000-year window that we have to transmit information to the universe. We think that 2,000 years is a pretty good estimate for any civilization. Then this is us. How long, how wide a view do we have of other civilizations? Where must they be if L is 2,000 for us to see them? And the answer, there. And if you didn't see anything, that's because it was a very small change. Right? But even if they're no longer existing, even if, okay, they lasted their 2,000 years and then they fell into their computers and that was the last they transmitted, the distances involved, the distances in our galaxy are so unbelievably large that the likelihood of us seeing a signal from another civilization while we are listening is almost infinitesimally small. Again, another fantastic comic. SMBC, highly recommended. How's that? But, of course, at the moment, all of this is just, it's more philosophy than astronomy. Because we don't understand what most of these parameters that we were talking about are. But I'd like to leave you with one last astronomy fact before the end of this talk. And that's that everything I've told you tonight, everything we've discussed tonight, has been about the Milky Way galaxy. It's been about our galaxy. But of course, we're not the only galaxy out there. If you take some of the most powerful telescopes on the planet and you point them in an area of the sky that is less than 1% of the total, and you look for galaxies to just a fraction of the distance to the edge of the visible universe, this is what you see. Every single prick of light in this image is a real, documented, seen galaxy. We have observed them, we have mapped them, and we have placed them in three-dimensional real space where they are. Every one with billions of stars, billions of habitable Earths, billions of places where life could sprout. And so to sit in and amongst the enormity of that which is the universe, and to think that we are alone, to me, is unthinkable. That's all.
Awesome talk. Thank you very much. So now, Dr. Angus will take questions. So bombard him.
Gerne auch auf Deutsch übersetzen.
Just Angus is fine.
Well, I want to congratulate you on the splendid and brilliant talk, first of all.
Thank you very much.
I have only a couple of comments on that. Hailing from radio astronomy, I would like to sort of point out that one of the many reasons that we did not detect anything via SAT is the difficulty of detecting an artificial signal over distances of more than a few light years.
Absolutely. Yeah.
It will actually sort of vanish at the background noise, and if it doesn't vanish, it can't transmit any information.
Yeah.
So that is the first problem that we have. The second one that I would like to sort of comment on, that this is all still a very anthropocentric way of looking at things.
Absolutely.
You basically pointed to the problem and saying that a technological civilization might actually sort of extinguish itself in a very short time scale. But it is conceivable that we have intelligent life forms abundant everywhere, and they have avoided the technological trap. Just look at life forms on our planet like termites or something like that. They could easily evolve into something without ever needing any great technology, but they live in balance with their environment. They don't destroy their planet or anything like that. And these are the really intelligent life forms. I would like to sort of
You're absolutely on money with that one.
Anyone else? I have a question about your visualization.
Yeah.
How long does it take to take all this data? How easy is for astronomers to see a little slice of the universe?
Well, for this particular data, it is very, very long, is the answer. But that's a commendation to the quality of this particular data set. In general, the distance that you want to see into the universe or into the galaxy or anything is what determines the time that it takes to make those observations. And that's essentially because as you take something that is nearby and you move it further away that is emitting light, it gets fainter and fainter and fainter and fainter and fainter. And in order to be able to see that extremely faint thing, you have to take longer and longer and longer and longer observations with your telescope. So this data, in a wide field of view out to a reasonably moderate distance in the universe, takes a considerable amount of time. Narrow stuff that only goes the same distance takes a lot less. But yes, it's a considerable amount of effort.
So how many
So
years?
keep it I couldn't tell you. It would be a guess. Many.
Any more questions, please? Yes.
Would you like to?
So the question was, is anyone actually searching for extraterrestrial life? The answer is absolutely they are. So there is a very large community of SETI astronomers all over the world. And most of them work in the radio part of the spectrum, so not the optical that I was showing here. And the reason for that is because the most abundant signal in and around us is that from neutral hydrogen. And neutral hydrogen emits very strongly at a wavelength of 21 centimeters, which is in the radio. And so many, many, many years ago, when SETI was first thought of, people hypothesized that an intelligent civilization that was trying to communicate with other intelligent civilizations would use this 21 centimeter line as a marker for communicating with other parts of the galaxy. And so that's one of the main reasons why they use 21 centimeter search kits. And so there's radio telescopes all over the world, from Puerto Rico to Australia to Europe, that are performing SETI searches. And it's been going on for upwards of half a century.
Great. Any more questions? If not, we will thank Angus once more. Now we will have a small 10-minute break, but before the break, where you can order some more beer for the second talk, which will be in German. We have prepared a quiz for you, so we'll hand out some spreadsheets. Enrico will distribute them, and some pens, and Anna on the other side. And we'll give you some pens. And
Probably get them wrong. Probably get them wrong.
this is the quiz. Pens and so we'll collect them at the end of the break, and we will announce the winners. And the lucky winners can win some products we have from Euclid, glasses, or from the Argelander-Institut, some mugs, very nice notebooks, and a bag.
Genau, wir machen jetzt eine 10-minütige kurze Pause. In der Zeit könnt ihr mir Bier bestellen. Ihr könnt auch unser Quiz ausfüllen. Das Quiz wird gerade rumgegeben. Das ist sehr einfach und auch auf Deutsch. Einmal Englisch, einmal auf Deutsch. Der Gewinner oder die Gewinnerin kann wunderbare Preise gewinnen, die wir hier vorne auch ausgestellt haben. Also macht gerne mit.
So we also have some free stuff to give you, like stickers. So you can come here and help yourselves in the front. You can also talk to all the astronomers online. Yes. And of course, we want to print out some Astronomy on Tap related material, so we ask for your kind donations. We will circulate 2 glasses with 2 different designs, and which one you like the most? Put mine in here, so we make it for you and we give it to you for free next time.
Ihr könnt hier auch Sticker mitnehmen und Postkarten. Und wenn es euch bisher gefallen hat, dann würden wir uns über eine Spende freuen. Und mit der Spende möchten wir gerne Sticker produzieren und Anstecker. Und ihr könnt euch das Design selber auswählen. Einfach das Geld da reinschmeißen, wo euch das Design besser gefällt.
And also we have a surprise for you today. The ones that are into Instagram can take a photo. Okay, so you take a photo, you post it on Instagram with the hashtag Bonn, and on our next event in October, we pick one like a winner that wins a big prize. Okay.
Genau, wenn ihr ein Foto mit unserem Instagram-Namen macht und es auf Instagram mit unserem Hashtag taggt, dann wählt ihr vielleicht euer Bild aus und ihr bekommt einen Preis im nächsten Event im Oktober.
So we will be back in 10-15 minutes.
Anna, I have more pens. They don't work.
We'll try to keep them for the next time.
No, the theory was that people told me that they take that. I voted against that idea, but if anything, just promote the stuff there.
I want a sticker. Do you want to? The universe is my day. How funny. Yeah. Take it.
Would you be interested in a Extraterrestrial calendar? Only the hottest astronomers and all year.
Damn. Love that.
Doesn't that turn you on?
My goodness.
A raging hard.
She'll never stop talking. Yes. You have to have name. Oh, okay. What is the equivalent of a name?
You will be there. You will be this one.
What? We can do it. I didn't think that. Candy? Yeah, but I guess
dark forest. It's like so the idea is that maybe it doesn't.
I think I reported like 2 seconds or something.
I don't know what's wrong.
That's not your main action. But I think the whole thing is now it's very difficult to follow.
One as well.
I mean, it's
Okay, I need to find
We were just taking pictures in front of the light.
Small test.
And After the last.
Hello, we will start again in 2 minutes. Okay? In 2 minutes.
So how they do it? Just all right. That's okay. You're still coming in every day. But if somebody wants to talk, get in touch.
You're back. I hope you enjoyed our first talk and break, and you had the chance to take a photo with our Insta frame. And if you did, you can post it on Instagram, tag us with the hashtag and our account. And next month, we will pick one, the best, and give out a prize to the winner.
Ja, für jeden, der noch kein Foto gemacht hat mit unserem ganz tollen Instagram-Frame, macht noch ein Foto, postet es, taggt uns und wir wählen das beste Foto aus. Und es gibt Preise dafür.
Also, I hope you like the quizzes prepared by Sandra. So, we collected this, or if you haven't given it back, please give it back to us. And we will announce the winner at the end of the second talk. We will give out the prizes.
Ja, wenn ihr euer Quiz noch nicht abgegeben habt, dann gebt das bitte jetzt ab. Wir werten das schnell aus und der Gewinner oder die Gewinnerin wird am Ende des zweiten Vortrags bekannt gegeben. Also, jeder, der es noch nicht abgegeben hat, schnell abgeben.
So, yes. It'd be good to take it away. So, our second speaker of the night is Sandra Unruh, PhD candidate, also at the Argelander-Institut of Astronomy. Ms. Unruh did her master's in astrophysics here in Bonn and is an expert on gravitational lensing. Today she will talk to us about gold in the universe and where we can find it. So get ready to pack your bags for an awesome trip to outer space.
Ja, unser zweiter Vortrag ist von Sandra Unruh. Frau Unruh hat ihren Master hier in Bonn absolviert, am Argelander-Institut, wo sie jetzt auch Doktorandin ist. Sie ist eine Expertin für Gravitationslinsen und heute wird sie über interstellare Goldminen reden und darüber, wo wir Gold finden können im Universum. Also packt eure Sachen für einen aufregenden Trip ins Weltall mit Sandra Unruh. Und ja, also der Vortrag jetzt wird auf Deutsch sein. Ich hoffe, das ist nicht so ein Problem für die meisten. Ja, und es ist auf jeden Fall eine große Ehre, dass ich hier sein kann. Und so viele Leute sind hier, das ist der absolute Wahnsinn. Und jetzt noch den Präsenter finde. Dann können wir auch schon loslegen. So, das hier ein Astronomie-Event, deswegen direkt erste Folie. Periodensystem der Elemente. Alle nochmal in euch gehen, damals der Chemieunterricht, all die schönen Erinnerungen. Ihr müsst euch nicht viel erinnern vom Chemieunterricht damals. Alles, was wir heute brauchen, ist, warum diese Elemente in der Reihenfolge angeordnet sind, wie sie angeordnet sind. Oben links bei jedem Element sieht man die kleinen Zahlen, 1, 2, 3, 4 und so weiter. Ich hoffe, jeder erinnert sich, das ist die Anzahl der Protonen im Kern. Im Kern sind sowohl Protonen als auch Neutronen. Und je nachdem, wie viele Protonen im Kern sind, da tun wir das Element dann hin. Und dann die Chemiker haben immer viel zu tun, ordnen das dann noch ein, Metalle, halt Metalle, Edelgase, Halogene und so weiter. Das ist heute alles total egal. Die Frage, die ich mit euch zusammen klären will, hier heute Abend, ist, wo kommen die Elemente eigentlich her? Wir bestehen definitiv aus ziemlich vielen von diesen Elementen. Man muss genug Magnesium zu sich nehmen, im Salz des Natrium. Wir bestehen auf Kohlenstoff, kohlenstoffbasiertes Leben. Wo kommt das alles her? Da verrate ich schon mal, gehen wir zurück zum Anfang. Nicht zum Anfang von heute, nicht zum Anfang von eurem Leben, nicht zum Anfang der Erde, zum Anfang des Universums. Und dann 3 Minuten später. Also als das ganze Universum 3 Minuten alt war, da gab es genau 2 Elemente. 3. Fast 75% Wasserstoff, oben links ein Proton im Kern. und 25% Helium, 2 Protonen im Kern und fast vernachlässigbar, aber immer noch ein bisschen Lithium, 3 Protonen im Kern. Und ich könnte den Vortrag über jedes Element quasi machen, aber ich dachte, Gold kennt man, Gold, da kann man drin investieren, das ist stabil, da können wir uns heute mal mit befassen, wo es herkommt. Und Gold hat die Zahl 79, es hat 79 Protonen im Kern und wir versuchen heute mal rauszufinden, wo kommt denn das Gold her? Also wie gesagt, der Anfang, wir sind bei 3 Protonen direkt nach dem Urknall. So, und jetzt besuchen wir diese ganzen astrophysikalisch wichtigen Orte, wo das passiert. Und mit Besuchen meine ich zeige euch ein paar Bilder, den Rest stellt euch vor. Alles andere kostet zu viel Zeit und zu viel Geld. Wir wollen ja alle heute nach Hause. Also Achtung, ich weiß, es ist ein schwieriges Schaubild, aber das ist meine sehr wissenschaftliche Repräsentation, wie so ein Stern aussieht. Ja. Wir haben einen eigenen Stern, unseren Haus- und Hofstern, gemeinhin als Sonne bekannt. Und das weiß man vielleicht noch, die Sonne bezieht ihre Energie aus Kernfusion. Kernfusion aus 4 Wasserstoffteilchen zu einem Heliumkern. Und weil es da eine Massendifferenz gibt, weil 4 Protonen weniger schwer sind als ein Helium, wird dabei Energie frei und diese Energie drückt nach außen. Ja? Also der Stern wird quasi so von innen heraus, gibt es einen Druck nach außen, von außen gibt es den Gravitationsdruck nach innen. Gravitation, das, was uns hier auch am Boden hält. Ja. Und so entsteht ein Gleichgewicht und wir haben einen schönen Stern und dabei wird Wasserstoff zu Helium fusioniert. Helium hatten wir schon, nicht so interessant. Aber irgendwann ist das Wasserstoff alle im Kern und nur noch Helium da. Und dann machen die meisten Sterne Folgendes, sie fusionieren Helium. Und zwar zu Kohlenstoff und zu Sauerstoff. Das Ganze ist ein ziemlich explosiver Prozess und dabei wird die äußere Hülle von dem Stern ein bisschen nach außen gedrückt. Es entsteht ein sogenannter roter Riese. Und auch unsere Sonne wird in 4-5 Milliarden Jahren roter Riese werden. Und auch noch die Venus verschluckt. Und in der Mitte wird dann Helium zu Kohlenstoff und Sauerstoff fusioniert. Sauerstoff hat die Protonenzahl 8. Dann ist Ende. Was dann passiert ist, es gibt einfach keine Fusion mehr und die äußeren Schichten fliegen einfach weiter vom Stern weg, relativ langsam mit ungefähr 700.000 Kilometer pro Stunde. Fliegt einfach der äußere Teil dieses Sterns weg, von unserer Sonne zum Beispiel, und in der Mitte bleibt zurück ein weißer Zwerg. Und der weiße Zwerg besteht aus Kohlenstoff und Sauerstoff. Und das war's. Das machen viele Sterne, das macht unsere Sonne. Wir haben total 0815 Sterne. Also was so Sternentwicklung angeht, ungefähr das Langweiligste, was es gibt. Ist aber ganz gut, das macht ihn relativ stabil. So, alles klar. Also das war nicht die Lösung, sich bei Sternen umzugucken, die so schwer sind wie unsere Sonne. Also nehmen wir mal die nächsten Sterne, die ein bisschen schwerer sind, sagen wir mal 10-mal so schwer wie die Sonne. Wie ich ja schon erklärt habe, Sterne brennen in ihrem inneren Wasserstoff, hatten wir. Wasserstoff brennt zu Helium, Helium brennt zu Kohlenstoff und Sauerstoff und dann ist bei unsere Sonne Ente. Aber schwerere Sterne können noch mehr. Die machen da nicht Stopp, die brennen dann auch noch Kohlenstoff und Sauerstoff zu Neon, zu Magnesium, zu Silizium und irgendwann zu Eisen. So. Und da ist dann wieder Stopp. Warum ist das Stopp? Wie ich am Anfang gesagt habe, es wird was verbrannt, damit Energie frei wird. Das heißt, Kernfusion erzeugt Energie. Aber jeder von euch weiß auch, dass auch Kernspaltung Energie erzeugt. Zum Beispiel von Uran. Das ist jetzt nicht die präferierte Energieerzeugung, aber darum geht es heute auch gar nicht. Und das heißt, wenn sowohl Kernfusion als auch Kernspaltung Energie erzeugt, muss es irgendwo in der Mitte einen Punkt geben, wo sich genau beides aufhebt. Und dieser Punkt ist Eisen. Wenn ich Eisen versuche zu fusionieren, dann verbrauche ich plötzlich Energie. Und deswegen geht es einfach nicht nach Eisen. Nach Eisen ist Stopp. Eisen hat die Protonenzahl 26. Wir sind also immer noch ein ganzes Stückchen weg. Aber da gibt es noch ein paar Sachen, die wir im Petto haben, die Astronomie. Jetzt kommen die interessanten Sachen. Also, vorhin hatten wir unsere sonnenähnliche Stern, hört auf zu fusionieren, die äußeren Schichten fliegen einfach weg, relativ langsam, 700.000 Kilometer pro Stunde. Jetzt passiert viel mehr.
Plötzlich haben wir diesen roten Riesen, der in der Mitte nur noch einen Eisenkern hat. Wir können Eisen nicht fusionieren. Innerhalb von einer Millisekunde zieht sich dieser Kern so nah zusammen, dass Protonen und Elektronen verschmelzen zu Neutronen. Das ganze Ding wird inkompressibel, es wird so dicht, dass man es nicht dichter machen kann. Es wird so dicht, wie ein Atomkern selbst dicht ist. Ja? Also es werden einfach Nukleon an Nukleon gepackt. Die äußeren Schichten fallen aber weiterhin auf den Kern ein und dann passiert dasselbe, wie man einen Flummi so mit voller Wucht auf den Boden wirft. Das Ganze fliegt auf den Boden und wird nach oben geschossen. Und in dem Fall von einem Stern halt in alle Richtungen und das nennen wir dann eine Supernova. Bei einer Supernova haben wir mit Millionen Kilometer pro Stunde Gase, die nach außen fliegen. Ja. Ja, die großen Zahlen, da sind sie wieder. Von denen haben wir eben gelernt. Aber jetzt können wir sie ein bisschen in Perspektive bringen, deswegen habe ich angefangen mit den langweiligen weißen Zwergen und gearbeitet und so vor. Die Supernova, Millionen Kilometer pro Stunde, werden hier Teilchen nach außen geschleudert, die dann mit dem umliegenden Gas kollidieren und das setzt genug Energie frei, um weitere Fusionsprozesse in Gang zu setzen. Allerdings, da müsst ihr mir jetzt einfach glauben, wie immer, eigentlich schon. Das geht nur bis Rubidium und wie wir alle wissen, hat Rubidium die Protonenzahl.
37.
Wow. 37. Und 37 ist immer noch verdammt weit weg von 79. Und das war lange debattiert. Es gab einige Theorien dazu, wo die ganzen schwereren Elemente herkommen. Und letztes Jahr gab es die ersten Beobachtungen dazu. Und zwar folgendes. Also wir haben eine Supernova, das ist das gesamte Material, was halt am Stern außen ist, was nach draußen geschleudert wird. Und ich habe schon gesagt, in der Mitte bleibt ein Kern übrig, voll von Neutronen. Und den nennen wir Astronomie. Wir haben es immer richtig drauf in Namensfindung, Neutronensterne. Neutronensterne sind so groß, so 20 Kilometer Umfang, passt also relativ gemütlich auf die Fläche von Bonn, ist aber meistens so doppelt so schwer wie die Sonne. Und die Sonne ist so schwer, Achtung, wieder große Zahlen, 2,30 Kilogramm. Ja. Und davon das Ganze zusammengepresst auf die Fläche von Bonn. Also nicht schlecht. Und jetzt brauchen wir nicht nur einen davon, das wäre jetzt langweilig, wir nehmen zwei. Und das Ganze nennen wir dann Doppelneutronensterne. Und Doppelneutronensterne könnten irgendwann mal vor vielen Milliarden Jahren entstanden sein. Einfach, es gab ein Doppelsternsystem vorher, beide Sterne sind in der Supernova explodiert, es blieben zwei Neutronensterne als Rest übrig, die sich dann umkreisen. Und während sie sich so umkreisen, verlieren sie nach und nach Energie durch die Aussendung von Gravitationswellen und dann kommen sie sich näher und näher und näher mit gemütlichen Geschwindigkeiten von so 10% der Lichtgeschwindigkeit, so 100 Millionen Kilometer pro Stunde. Und dann krachen zweimal die Masse der Sonne jeweils mit 100 Millionen km/h aufeinander. Jeder kann sich so vorstellen, eine normale Kollision, weiß ich nicht, Rollator in eine Menschenmenge, zwei Autos gegeneinander, zwei Neutronensterne mit 100 Millionen km/h gegeneinander und da wird richtig Energie frei. Und jetzt war der Name Supernova schon belegt, Supernova übrigens auch. Wir sind uns niemals so schade, wir haben es Kilonova genannt. Und es entsteht dann eine sogenannte Kilonova. Und in der Kilonova wurde dann postuliert, können so ziemlich alle weiteren Elemente entstehen, unter anderem auch unser Gold. Und der Grund, warum ich euch heute davon erzähle, ist, dass wir es letztes Jahr im August das erste Mal beobachtet haben. Und mit das erste Mal beobachtet meine ich nicht, dass da eine Gruppe von Astronomen gab, die das gesehen haben. Das war von der gesamten Community auf der Erde, die was mit Beobachtung der Astronomie machen. Also alle Astronomen davon haben sich 1/3 nur allein mit diesem Event beschäftigt. Allen voran, Nobelpreis für Physik dieses Jahr, Gravitationswellen-Event, LIGO in den USA und Virgo in Italien. Ich habe da leider keine Zeit, weiter drauf einzugehen. Aber vielleicht können wir irgendwann mal in Zukunft einen Gravitationswellen-Vortrag hier machen. ganz interessant ist. 1,3 Sekunden später der Fermi-Satellit im Weltall, der misst Gammastrahlen, die energiereichste Strahlung, die wir haben im Universum. Ebenfalls, und innerhalb von wenigen Stunden gab es dann, also da gibt es so ein Netzwerk und dann macht man einen Alert, einen Alarm. Und jedes einzelne Teleskop, das funktionsbereit war, hat versucht, sich dieses eine Event anzugucken. Und da hätten wir, zum Beispiel im UV-Bereich NuSTAR und Chandra, im optischen Bereich weitere 5 Teleskope, Hubble Space Teleskop, PanSTARRS, VLT, Atlas, im Infraroten, VISTA und Spitzer und VLT und wieder das Hubble Space Teleskop und schließlich im Radiobereich, was wir auch hier in der Nähe haben, in Effelsberg, die 100 Meter, das 100 Meter Radioteleskop kann man sich angucken. Und das waren über 75 Kameras, die sich dieses eine Event angeguckt haben für ungefähr 20 Tage. Und das ist so ein kleines Sammelsurium von den Daten. Und dabei haben wir dann auch untersucht, welche genau entstanden. Und dabei haben wir das Gold dann auch gefunden. Das ist jetzt sozusagen als kleine Zusammenfassung. Wir haben angefangen mit Wasserstoff und Helium vom Urknall. Dann haben wir uns ein bisschen mit Sternenexplosionen beschäftigt. Das ist das Gelbe und das Weiße. Und alles, was hier unten lila zu sehen ist, ist zum ersten Mal in der Geschichte der Menschheit letztes Jahr im August beobachtet worden bei der Kollision von 2 Neutronensternen. Und da ist das Gold dann auch dabei. Das Ganze ist nur 100 Millionen Lichtjahre entfernt. Also kein Problem. Ja, können wir alles einsammeln. Da sind Massen, Tonnen über Tonnen über Tonnen entstanden. Wir müssen ja nicht nur das Gold einsammeln, wir nehmen einfach alles mit. Wir sind unglaublich reich. Wenn wir wiederkommen, ist die Erde vielleicht schon zerstört. Aber das war ungefähr alles, was ich dazu sagen wollte. Noch eine kleine Summary, manchmal in Englisch, for all of those people who didn't understand anything. So if you go home and people ask you what you learned about, you're like, yeah, there was something with ET. And then there was this girl, and she told us about that all the light elements in the universe are either created in the Big Bang or in nuclear fusion stars, and all the heavy elements are somehow created when something explodes. I think there were neutron stars involved. And you came for astronomy, but you get a stock advice. Please don't invest in gold. Now that we found a new source, we can harvest this all. This will drop the price of gold soon. So like in a million of years. Yeah. So be aware of this. Thank you very much.
Ja, vielen Dank für den Vortrag und vor allen Dingen für den schönen Rat dazu, nicht in Gold zu investieren. Gibt es Fragen? Other questions also in English? No questions? Yeah, if there are no questions, then you have a question?
So, I don't speak German, so I don't know what you said. But that said, where should I look for gold? Just in the universe.
Okay, I think there are 2 options. Either you find some neutron stars, preferably a double neutron star, and you wait some billion of years until they collide. Or you find a site where this already happened, and then you just go there, collect your gold, come back, maybe some time travel, and I think that's it.
Any other question? Maybe smarter than us. No? Okay, so then I think we can go on, and it's about time to know the answer to the quiz. So actually, Sandra is going to present you again the answer. So I just give to her the microphone.
Genau, es wird jetzt Zeit, die Gewinner von unserem Quiz festzustellen. Und ich glaube, wir Sandra uns jetzt die Antworten vorstellen auf die Fragen, die wir im Quiz haben, und danach wird die Gewinnerin bekannt geben.
So, it's me again. This time I'm a little bit less nervous because now everything's on the screen that I gotta say. And I hope you all enjoyed the quiz. We enjoyed making it. Yeah, so I give all the solutions in English. I think that's for most of the people. So first, what is the name of our galaxy? Okay, 1, 2, 3. All right. Second, what is the equivalent of a day? 1, 2, 3. Yes. Everyone said that. So Earth takes one time around itself. For some people, it's different, but let's just stick to that for the quiz now. Third question: which 12th planet exists between Mars and Jupiter? Exactly. It's the last option. We're never sure how to pronounce it, that's why I just leave the voice here from the left shouting it.
They said Santa.
What?
I also said Santa.
I'm shocked. They said wrong answers. Wow. Okay. No answers from there, please. A lunar eclipse occurs during which moon phase? Exactly, it's Sailor Moon. Of course, it's full moon. Why is it not new moon? Because at new moon you can't see the moon anyway. Next question: what's a light year? I think people just want to go home. So it's the distance light travels in a year. 6 questions. Why do astronauts on the ISS float? No advertisement here intended. It's because they are constantly falling. I think one of the hardest questions today here. So if you're not an astronomer and didn't do that immediately, you either watched The Mouse 3 weeks ago, or you're just smart. So 7, why are heavy elements such as gold found? And everyone knows that. It's not NASA's secret nuclear fusion facilities. It's stellar explosions of some kind, general answer. 8th question, now a bit more to Angus talk. What do we call the apparent discrepancy between the lack of evidence but the high probability estimates for the existence of extraterrestrial life? Tom Riddle! The Harry Potter reference! It's a Fermi Paradox. 9. Which astronomer created a formula for measuring the prevalence of extraterrestrial intelligence? I had to Google the joke here. Who gets the joke?
I do.
Yeah, you made the joke. Please tell us.
Aubrey Graham is Drake.
And last question, the most important. I hope we see all of you next week here, next month. We can also meet next week, but it's more unofficial. So when will Astronomy on Tap be held? It's of course every last Tuesday of the month, except December because that's Christmas.
Just bring us to the end of tonight. I would like to thank you all for being here, and I hope to see you again next time. And while I encourage you to come here, to take picture and take some free stuff from here. It's now about time to tell you who won the day quiz.
Okay. Jetzt der Gewinner vom Quiz.
So we have 4 winners today. Number 1 is the group called Pluto is a Planet. So one of you can come to the front and make a prize and a clap for them. So you can choose between a mug, a bag, a notebook,
I think I was
and a glass.
Notebook. Notebook.
Yeah. Number 2, we got nuclear. So we have a mug, a glass, or a bag. Okay. Third, we have Annika, Philip, Marcel, and Sheldon. So you get a glass or a bag.
Glass is the best.
Yes.
And last but not least, we get Sueca und Mini. Mini and someone else. Atsura. Atsura and Yara. Yes. So, number 4. So you get a bag.
So just a quick reminder that we are on all main social media. So, well, actually, if you want a picture, there is a frame here. You can take a picture, take some something that you like from this table. It's free, and just tag us on the main social media. And please remember that we have Astronomy on Tap here every last Tuesday of the month. So next time around, the 30th of October, the 17th.
Genau, falls ihr informiert bleiben wollt über unsere weiteren Events, könnt ihr uns gerne folgen auf Facebook, Twitter, Instagram. Könnt gerne noch ein Foto mit unserem tollen Frame machen. Ja, wie gesagt, Astronomy on Tap wird immer am letzten Dienstag am Monat hier stattfinden, außer im Dezember. Und das nächste Event ist am 30. Oktober. Also vielen Dank, dass ihr hier wart und wir würden uns freuen, euch wieder zu sehen.
Thank you very much.
If I can so I guess we go in straight.
Yeah, of course. He just said that there's so many that they can't see that they have it.